Okay, so let's talk about complexity. So for the sake of complexity, I think as developers, we have this very interesting, and that interesting is in quotes, relationship with complexity. From Neil Ford. Developers are drawn to complexity like moths to a flame, often with the same outcome. And I've been writing about complexity, simplicity, and all these things for a very long time. I'd like to think it's made some kind of difference. But today what I want to talk about is I want to talk about the landscape of complexity, including some examples. I'm not just going to have a rant about C++, shooting fish in a barrel and all that. But I will mention a couple of things. So here's something. This is Exe from 1999. This is an image processor. This is Ricky Mazzullo, and that's Pancho the chimp. This is 1974. This image is adapted from. She's teaching Pancho eating etiquette. Look, mouth, and she's teaching Western eating etiquette about not leaning over and taking things from somebody else's plate. And they taught Pancho sign language. So she's teaching that. So there's a communication issue. But right down here, somewhere down here, simple, not simplistic. So I had a think piece in this one called For the Sake of Simplicity. So I've chosen the opposite title here, For the Sake of Complexity. And the way I looked at it, and I still look at it from this point of view, the inherent complexity of a software system is related to the problem it is trying to solve. The actual complexity of a software system is related to the size and structure of the software system as built. And that's kind of an interesting one. There is this idea that whatever you are working on, the nature of the domain has a kind of there's an absolute minimum you can't get below. Otherwise, your solution is simplistic. You've missed out really important things from the domain. But our ability to add, oh my goodness, we have skills. Or do we? Because the counterpoint here is the difference between the two is a measure of our inability to match the solution to the problem. How often do we not match it appropriately? Now, this is also a riff on an idea, from the Mythical Man Month, what doesn't ultimately, find its source in the Mythical Man Month. And this is still a very relevant book, particularly the second edition. I kind of find it interesting because sometimes it is possibly the most cited book in the whole of software development, but many people haven't read it. It's fascinating from a historical point of view. It's a 1970s book written about a 1960s project. That feels incredibly remote, except for the fact that humans have not really changed, it turns out. The hardware, oh yeah, all that's changed. So there's some wonderful history. You look at the things that have changed, and then you look at the things that haven't changed. And you go, yep, still human. Yep, we're still here doing the same things. We have not been updated. And so I read the original version in the 1980s. In the 1980s, Fred Brooks also published a series of papers, including one on no silver bullet, the idea that there is no silver bullet to solve all of your problems. The anniversary edition, published in the 90s, includes that and a number of other things. One of the ones that was included is on essence and accident in software. And he talks about this, he takes a slightly different view. He talks about the essential complexity and the accidental. The accidental is the stuff that doesn't have to be there, that's a nature of our design choices. And he asked this question. So he asked this question in the 1980s. How much of what software engineers now do is still devoted to the accidental as opposed to the essential? And that question's still good today. When you're sitting down, how much is actually to do with the target of whatever it is you're supposed to be releasing? How much is actually to do with the feature set? And how much is to do with the complexity, often that came from the past, previous design decisions, either directly or indirectly? It doesn't have to be you. It could be people who no longer work with you. It could be people who are still working with you. It could be you. The point there is all of that complexity is optional. Now, actually, a better breakdown of the essential and accidental, I won't use Fred Brooks' definition because it's a little bit ambiguous. I found a better one was a revisit in Ben Mosley's and Peter Marks's Out of the Tar Pit, although I don't necessarily agree with the conclusions of that particular paper. It's a really interesting read in terms of how they approach things, but they gave very crisp definitions. Essential complexity is inherent in and the essence of the problem. That's why we're building this product. That's kind of the nature of the domain. as seen by the users or product owners or whatever. Accidental complexity is all the rest. Turns out there's an awful lot of all the rest. Complexity with which the development team would not have to deal in the ideal world. Performance issues, suboptimal language, infrastructure, unmanaged technical debt, all of this kind of stuff. In other words, there's an awful lot that we do by accident. Now, there's a counterpoint here. There's an interesting thing. The Manifesto for Agile Software Development, the 4 values, let's skip that because there's another thing. There's 12 principles. People really struggle with this one. We've ended up with an industry that values processes and tools over individuals and interactions, we seem to have come full cycle. But I won't rant about that one today. There is, in the principles described, there is this listing here, simplicity, which we regard as the counterpoint, the counterbalance, the opposite almost of complexity. The art of maximizing the amount of work not done is essential. Now, there's 2 good things and 1 bad thing here. The 1 bad thing is that is not the definition of simplicity, not even remotely. So let's get rid of that. Simplicity is essential. 2 good things. This is good. Maximizing the amount of work not done is essential. These are two separate things. If you get it right, they're related, but they are not equivalent. So there is a thought here. How do we talk about these things? I haven't told you what I mean by simplicity or complexity yet. And it's interesting because these words have a number of different definitions. So I'll go back to a conversation I had with a colleague a number of years ago called Paul. We were both working on a workshop, example for a workshop. And so basically, this is kind of like an A/B test in one sense. We both came up with solutions. And he looked at my solution and said, oh, my solution's simpler than yours, Kevlin. And we kind of sketched it out. I said, I don't think it is, Paul. He said, well, yeah, mine's simpler because I've got kind of 6 classes. Whereas, drawn to scale, you've got 15. He thought he was relating complexity to just raw number. I think that's for you. He was relating it to just raw number. That's not, although the numbers matter, that's too simple or simplistic a definition of complexity. What you really need to understand is the relationships. It's the number of things and the number of relationships. That's kind of Paul's code, and I might have left out a couple. I mean, there was no doubt everything depended on everything else. I've been generous by leaving out a couple of everythings. Whereas mine kind of, radiated out from the center and had reasonable control structure and factored and all the rest of it. We had 2 very different ways of looking at the universe. But from his point of view, he ended up with more lines of code and everything did everything, but he had fewer classes. He had fewer files to check in. So therefore it was simpler in that perspective. Whereas when you start working with a system, you realize actually it's the interconnections that kill you. That's the bit that's going to get you. It's the, I'd like to work on this, how much else do I need to know? This is an interesting thing because you can get it's kind of an illusion of size. You can work on a 100,000 line code base and it can seem enormous if it's tightly coupled. But you can also work on a 1,000,000 line code base and it can seem small because of how it's loosely coupled. Pick a piece of code and say, what else do I have to know in order to work on this? And the closer to you that horizon is, the simpler it is. In other words, you can put it in your head. The system itself may be large, but now it's just like, no, it's all close. But do I have to know everything? The more that you are required to know everything, the more complex it is. Which gives us a kind of different way of looking at things. Many different and connected parts. There's the and, really important, the connection. Otherwise, if nothing's connected, honestly, it's really simple. You don't have to do anything. Not easy to understand, complicated. Now, sometimes we use the word complicated interchangeably with complex. Every now and then somebody will say, complex is not the same as complicated. And they're kind of right, and they're also kind of wrong. That's the problem. That's natural language for you. Sometimes we use these terms interchangeably. Sometimes we use the term complicated to refer to something that is less than complex. Sometimes we use the word complicated to refer to something that is unnecessarily complex. That's the way it's used in the Zen of Python, if you're familiar with that. So these words are a little bit flexible. The idea of not being able to understand something, of course, there's a sense of knowledge there. Some things are more complex than others because I just don't know about them. But that's not a property of the thing, that's a property of the you. We need to distinguish between these things, okay? But that idea, when we see it in noun form, hey, you know what? It's an interlinked system. Yeah. However, if we go digging through the dictionary, the noun form's great. The related group of repressed or partly repressed emotionally significant ideas which lead to abnormal mental states or behavior. Oh yeah, I've seen that in code, or I felt that with code. And a feeling of disproportionate anxiety about something. Yep, I think we've all felt that with code as well. So yeah, the word complex has very broad applicability. But that idea of interconnection, it's not a new one. That idea of interconnection and managing the connection. When we talk about dependencies, we often have a very simple idea of dependencies. We talk about dependencies, we might talk about header-to-header dependencies. Okay, we might talk about class-to-class dependencies, function-to-function. That's all the visible stuff, the stuff the IDE can tell you. But Parnas back in 1971 was talking much more broadly. The connections between modules are the assumptions which the modules make about each other. The assumptions goes beyond the things that are easily checked. So every now and then, for example, there's a discussion about thread safety. People say, is this code thread safe? All code is thread safe. You show me a piece of code and I will show you that it's thread safe. You're asking the wrong question. The question is, what do you mean by the context of this code? There's pieces of code that if you never executed them would be thread safe. The number of threads running through for this code to be safe, the number of threads running through it should be 0. For this code to be safe, the number of threads running through it should be no more than 1. Thread safety is, all code is thread safe. You just have to tell me the degree of safety that you wanted. Because every now and then, I need a thread safe class. Yeah, this one is. Just don't share the objects between different threads. It's thread safe. It's just fine. Otherwise, you end up with people putting locks everywhere. Ooh, that's interestingly complex. They create unnecessary complexity, accidental complexity. But that's an assumption. It's not stated. It's not a checkable, codable assumption. I'm assuming that you're working in a particular way. The problem is where we end up with differences. You can end up with hard-coded dependencies. We both have the same hard-coded dependency. If you look at these pieces of code, you'll see they have no dependency from one to another in terms of code. But the idea, how they talk to the database, the protocol that they use, they're tightly coupled. So dependencies are more than the easy stuff given to you by IDEs. In fact, if we look at dependencies broadly, that's our system, and that's the subsystem of interest. That's the one we're working on. When most people talk about dependencies, they're talking about the code that they own. I don't mean they individually, though it might be that. I mean they as an organization. There's a boundary there. This is our system. At some level, we own this code. Of course, we need to manage those dependencies. That's, but in their head, that's the common thing. Where people have blind spots is about the code that they don't own. And it's just like, oh yeah. So I've had this conversation with people. So what are your dependencies? And people go, oh yeah, here's the dependencies. All right. So you guys use Boost. Oh yeah, we use Boost. That's a dependency. Oh yeah, but it's just part of the platform. That doesn't mean it's not a dependency. It just means you have a name for it. And then people are really bad at the dependencies that their dependencies pull in, the transitive dependencies. And then the platform is a dependency. That means the programming language. I had this conversation with one group. I sort of, let's just sketch out the architecture. And it was interesting because I said, you haven't put any of the programming languages on these. Oh yeah, but that's just an implementation detail. I said, it really isn't. Because if I said tomorrow we're going to use a different programming language, you would tell me, oh no, we can't. Oh, a dependency is something that prevents or enables you from doing work. If I just suddenly said we're going to change language, it's just like we can't do that. Oh, why? Because everything depends on the fact that we're using a particular language. And I said, okay, so let's break down the languages. And it's just like, okay, now you're telling me something about the boundaries. This is C++, this is Python, this is Java. And I said, the next question is you haven't told me what versions of the language you're using. And they're going, really? I said, yeah, that's a dependency as well. This was just before Python 2 expired. So therefore, whether this is in Python 2 or Python 3 is significant. Because if you're using Python 2, I need to know why. Because if you're using Python 2 because somebody else's library is in Python 2 and therefore we can't migrate it to Python 3, that's a dependency that has changed your architecture. It's preventing you from doing work. If you're telling me, oh yeah, we've stopped at C++11 and we don't yet have a strategy for going to C++14 and beyond, then you have just told me something that is changing the shape of your work. That is a huge dependency. People are really blind to this stuff. And people often don't think of the operating system as a dependency. Some of you may know I collect photographs and images of software failures. The number of failures I see that people are still giving me for Windows operating systems that are no longer supported should be of deep concern for everybody because there's no security updates for these things. In other words, dependencies go all the way out. We're blind to these. We focus on, this is my language, I can see these in my IDE. Those I can't see, they're not important. Oh, they are. They tell you about the viability of your product in the long term. They are part of your architecture. I've had a couple of people say, what, you mean I have to know everything? But that's a lot of work. Hey, welcome to software development. But also, everything else. These other things, where does governance come from? It's not magically sprinkled over your system. Where is the demand for what you're doing? Because trust me, if there is no market for your product and you have no customers, you don't need to do anything. Fantastic, yeah? You don't need to do any bug reports or anything like that because nobody's using your product. You have to do no work at all. You might not get paid, but there's no work that you need to do. That's a dependency. And if the market says we're moving that way and you've got a product that's going that way, guess what? Welcome to dependencies. So dependencies are a rich domain. They add complexity. And in our case, they add complications. Now, this is something I discovered that's absolutely fascinating. I was running a workshop, it's only a few years back, and his father was a watchmaker. And Stefan mentioned, if I recall correctly, Stefan mentioned, did you know that in the world of watches, they have things called complications? And this is a selling feature. I'm kind of thinking we should think about that in software. This is the world's most complicated watch. Vacheron Constantin creates the world's most complicated watch, and they literally mean that. The Vacheron Constantin reference 57260 features a record-breaking 57 complications. I would love to see this in a code review. My class, I want you to review my class. I have 57 complications in this class. Yeah, I've decided I'm going to have an allocator because why not? Because everybody else does. I couldn't be bothered doing the work of my system, so I thought I'd add an allocator. And I've put a whole load of other stuff in here that's not necessary. All of these complications, magnificent. It's worth about $8 million. There's no hard and fast definition of a complication, but it generally includes any functions that go beyond simple timekeeping, like alternative calendars. There's even a little orrery built into this thing. All kinds of stuff, just like pretty much anything. There's probably even a C++ compiler in there. So let's look at something that has complications. So this is an interface. You know, I'm not expecting you to read it. It's intentionally in a small font. That's just to give you the impression of like, gosh, that's a lot. This is in Corba IDL. This is one of the interfaces that is defined by the Corba services, the collection service. This is an iterator. I mean, wow. I mean, this is not like an iterator. So something in C++, the STL style iterators effectively form a kind of calculus. They are actually useful. They create an integrated system of concepts, literally. This is just a bunch of people sitting around going like, well, maybe that'll be useful. It was designed by committee. Nobody ever actually wrote any code against this. The other thing is, what's fascinating about this is that you would never ever want this in a real distributed system. I would never ever want to be able to iterate over one element at a time with every single access costing a network access. That's why you do batch methods. You go, give me the next 1,000, give me the next 1,000,000. I do not want to go, get me the next one. Sitting there waiting for the network. Cool, I'm going to process this value. Now give me another one. You do not want to do it like that. So not only is this complicated, unnecessarily complex, it's also unnecessary. You would never actually want such a thing. So to quote SF author William Gibson, that which is over-designed Too highly specific, anticipates outcome. The anticipation of outcome guarantees, if not failure, the absence of grace. We see in a lot of code that the complexity does cause failure, but even when it doesn't directly cause failure, it is certainly graceless. But that's not the end of the story, because that's not the only interface in there. I want you to look at this and feast your eyes on the relationships between these interfaces. This solves a problem that nobody has. Okay, and this is a real problem. Software developers are very imaginative. They are very creative. And they will create problems that nobody has, or they will elevate their edge cases to be first-class mainstream usage. Another science fiction author, Paul Anderson, coined this thing, Anderson's law. I've yet to see any problem, however complicated, when you looked at it in the right way, did not become still more complicated. I believe that many C++ developers have this secretly pinned up in their workspace. I can do that. You've given me a simple problem. I can make that much more interesting. I'm going to submit something to Boost or the Standards Committee. Have you finished with that? Have you finished doing Hello World yet? I'm doing a Hello World framework, mate. It's going to be templated beyond belief. So there's a thing here. What we've got is a code smell, one of the classic code smells listed in Martin Fowler's original refactoring and in the new edition. Speculative generality. Speculation is one of the most powerful tools that human beings have. We should use it a lot. The ability to imagine alternative futures and possibilities is magnificent. The problem that we have is not our speculation, but what we do with that speculation. We have a nasty habit of putting it in the code directly before we need it. Speculation is a way of exploring possibilities. Choose the simpler one or hold it in reserve, but don't commit just yet. You get it when people say, oh, I think we need the ability to do this kind of thing someday, and thus want all sorts of hooks and special cases to handle things that aren't required. I offer you basic string, which astonishingly fails to live up to its name. I mean, it just about manages the string part, but basic, no. So I had a belief a long time ago that we should have just called it string, and that it should always be templated, because otherwise there'll be more character sets, and you really don't want to have to keep adding names to the standard every time a new character set comes along. You can call me Cassandra, because that's exactly what's happened. And then this noise, the traits, I mean, I've never been a fan of allocators. I love what people have been able to do with them since, but we'll get to that in a moment. I want to look at the char traits for a moment. The char traits were intentionally designed for, I don't know. We don't know why they're like this. Because why would I want to define all of these alternative orderings? This is trying to solve a locale and collation problem, which is not a type-based problem. It's one of those things, if you spend more than 5 minutes with this, you will either go mad, or you will understand, this is not how we solve this. You can't solve collation order at the character level. That's not a solvable thing. And it's also not a static type level thing. It is utterly the wrong abstraction. And every single class, every time somebody uses basic string, they are paying the cost for this complete fabrication. And then there's locale, which attempts to solve this. And you know, there are a couple of people who understand locale. And they wrote a book on it. And I think that's pretty much it. There's about 2 more people beyond that. This is an insanely complex solution. When I was a member of the BSI in the late 90s, the BSI C++ panel, locale was kind of one of those things. If anybody going to review this? Oh, no. Take 2 steps back. You just don't want to go there. Whatever problem it solves, we'd like to know. When it comes to memory management, if you sat down and said, I need to be able to customize the memory management of containers, the allocator model is almost precisely wrong. The number of useful allocators that have been written is surprisingly small. Probably most people, this room contains a very high density of people who might be able to understand it. It dilutes to almost homeopathic quantities once you go to the broader C++ community. Oh, it's something to do with allocation. And then they look at it and go, I have no idea what this is. It took years before anybody even came up with a useful alternative to the default, because it is exactly the wrong way of trying to solve this problem. And people have done masterful things with it, but by God, it's viral and messy and it's one of those things of like, we had a time machine, let's do this differently. It was introduced to solve a very different problem. And then people thought we could generalize it. It was used to solve the problem of DOS, denial of service. Also an operating system, denial of service. It was used to solve segmented memory in different memory models. And then somebody said, rather than saying, you know, there's a better way, there should be a better way of doing this, somebody said, maybe we could use it to have, like, deal with shared memory and, yeah, it turns out there are so many constraints that are now put in. The ability to do that is almost negligible. It's almost impossible. And rather than saying, you know, that didn't work out, we've left it in there. We're paying the cost every single time. So, observation. As someone who ends up building a lot of architectural infrastructure code, there's one thing I cannot emphasize enough. Do the simplest thing that works. Do not try to imagine future requirements or support ill-defined potential use cases. It will always change later. Always. Importantly, this is retweeted by John Carmack, and he just captured it really nicely. It's hard for less experienced developers to appreciate how rarely architecting for future requirements applications turns out net positive. I would also say experienced developers, because sometimes people don't get the feedback loop. You know that generalization you introduced 20 years ago that doesn't work, and the one 19 years ago that doesn't work, and the one 18 years ago. Sometimes people are not able to pick up on the fact that they're heading in the wrong direction because they're absorbed by the technical detail, which is lovely. So, is there a way to deal with this? Yeah. So I contributed to 97 Things Every Software Architect Should Know. One of the pieces I put in, it's also an extended versions on my blog, simplicity before generality, use before reuse. This is a really simple idea. It is incredibly difficult to put into practice because there is a nature that sometimes people, oh, but we can generalize it. The problem is, you can certainly write code that is too simplistic, too anchored to something specific. But it turns out that people don't have general problems. I mean, if they did, that would be fantastic. You know, if somebody said, we have a general problem, fantastic. Could you tell me anything about it? No, it's general. By definition, I can't. We want some software. What's it going to do? What do you need it to do? Give me your requirements. Oh, I don't know, something general. Brilliant. Here, have a compiler. This is so powerful, you can do anything with it. We've already solved this problem. The problem is that people have specific problems. Solve those, solve another one, solve those, keep it clean, keep the coupling down, try and get good names. And surprisingly, that is more likely to be future-proof than anything else. And one of the things that frustrates me sometimes when people are adding complexity to the code is they're missing the one thing. Oh, I'm future-proofing it. I'm making this available for the future. Have you written any tests yet? No, trust me. A bunch of code that has a load of parameters and a lot of complexity and no tests is not going to see a future. Okay? It's just like, well, the guy who wrote this before, he kind of left this. He said we could do anything with it. Yeah, how do you use it? I have no idea. Does it work? I have no idea. Okay, well, and I've seen that a few times. The best route to generality is through understanding known specific examples. It means we have to slow down, which is a problem in an industry where people keep encouraging you to go faster. In other words, much of our complexity is out of haste. Specific examples and focusing on their essence to find the essential common solution. A lot of use of the word essence tonight. So, simplicity through experience rather than generality through guesswork. This is a really important idea. Again, really hard to put into practice because our instincts might take us elsewhere. It suggests we should be doing something empirical. In other words, instead of going like, people might have this problem. I see this in lots of discussions. Oh, people might have this problem. I have a use case for this, I see very often. Great, but is your use case an edge case? In many cases, people add complexity for their edge case. It's kind of like they're nibbling at the edges, but fail to hit the heart of something. What is interesting is to then go and look at your code empirically. I do recommend this book by Adam Thornhill because he looks at your code empirically. The idea is we have all the data. This is actually one of the joys of legacy systems. Yes, I use the word joy and legacy system in the same sentence. Because a legacy system has history. You can find out what actually happens, not what you think happens. You can actually find out what happens by going and look at it. your code base. In fact, I'm going to say, just as a side, I hate the term repo for version control system. I mean, version control system's not great, but repo just belittles it. Oh, it's a repository. No, it's not. It's a time machine, which is way cooler. It's a difference engine, also cooler. It shows you what's actually happened to your system over time. It shows you how your system has behaved over time, what changes, what doesn't, what changes together. The data that can be mined from this is enormous. And like dependencies, we turn a blind eye to it. That's where you want to find out, what do we actually need to work on next? Where should we devote our architectural attention? So this is classic British architecture. It's a computer. I believe this is one of those kind of like innovative post-Brexit computer industry. This is Britain leading the way with new technology. It's certainly stable. It's monolithic. Hey, and twice a year it kind of works out. But please don't touch it. We're not entirely sure why it's there or why people used it, but just like a legacy system. Back in 1980, Meyer Lehman wrote this wonderful paper that is still surprisingly prescient and true, Programs, Life Cycles, and Laws of Software Evolution. As an evolving program is continually changed, its complexity reflecting deteriorating structure increases and less work is done to maintain or reduce it. These days, people have cut, so this is a wonderful observation. You have to put work in. It's a good physics metaphor as well. If you want to reduce the disorder, you have to put work into the system. Now, these days, we've struggled and played around with metaphors. We tend to use technical debt. I am very cautious about this. We need to be very careful with this term because people have started using the term technical debt just to mean shit I don't like. And that's not what it's there for. And sometimes people tell me that they've estimated their technical debt and they estimate it in either currency value or hours. And it's just like, no, you've misunderstood. That's not technical debt. It's not the cost of, it's not the cost of repayment. The whole point about the debt metaphor is the cost of owning the debt. These are not the same thing. The whole point of the debt metaphor is that sometimes you may take on debt intentionally, but remember, where does debt come from? It comes from borrowing. You are borrowing against yourself. When are you going to pay it back? What's your plan for repayment? Oh, I don't know. Who knows? Maybe somebody in the future, some other sucker, because I'm leaving tomorrow. The point there is that's not the original intention, although that is certainly a form of debt. It's unmanaged. The whole challenge of this, the message of the technical debt metaphor, it is not simply a measure of the specific work needed to repay. It's the additional time and effort added to all the past, present, and future work. That's the debt. That's why the debt metaphor matters. Because the longer you leave it, the more you have to pay. And the more resistance you will find, you end up paying the interest, but never the original amount. And that's the challenge. It's a huge source of complexity. It's the unmanagedness of technical debt. Technical debt is fine if it's managed. But unmanaged debt, that's the issue. So that's time. What about people? This is a diagram from one of the most influential papers ever published. How Do Committees Invent by Melvin Conway, 1968. Where he observed the basic thesis is organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. It doesn't have to be a commercial entity. It can be a non-commercial entity. It can be a committee structure. It can be anything. He made this observation, and we've had this verified time and again. He actually made this observation not because he's saying this is the doom of all systems. He said because, you know what? We found a criterion for the structuring of design organizations. Based on what we want to get out, we should arrange people in a way that reinforces that. We're not very good at this. People tend to regard the HR or the organizational aspect as somehow orthogonal, independent of the design they're producing. Whereas actually you can use this to reinforce this. If they ever cross, trust me, the people forces win. And there's this wonderful paper by Rob Smallshare, published in 2014, which I really think more people should read, where what he does is he explores, through a series of models, the relationship between people and code over time. Proportion of the code written by current team decays over time. It's kind of a nice decay model. In fact, what's interesting is that Rob then also shows you half-life. It works out is that it's half-life rather than worrying about any other kind of distribution. Absolutely fascinating. Turns out developers last significantly less than their lines of less time than their lines of code. Your lines of code will outlive you. The growth structure of your system will outlive those. Your CEO will probably be in that role for longer, but not as long as the lines of code. Applications are relatively short-lived, interestingly enough. FTSE 100 companies, I suspect since Rob did this in 2014, the FTSE 100, it's probably nudged down a bit. But there's a point here about understanding the relationship. It tells us that we are essentially, this model and this model, we are essentially programming in the past. If you sit down to do 8 hours of work, 7 hours of that at least is dealing with whatever was there before. We're not programming for the future. We're programming mostly in the past, which even on new systems, that can be slightly depressing to think about. But it's not, it shouldn't be a source of consternation, just something we acknowledge. And what's interesting is Rob then looks at the effect of what happens when people leave a team. Because even after somebody's left a team, it's like their code still exerts a pressure. It's like they're still there. So even if you have, and I think on this one, Rob had a team of 7 over 5 years. It's always a constant number of 7, but people leave. Over time, their influence, you can see when they leave, you get a black line, but the influence of their code lives on. It's a really interesting way of looking at it. But more importantly, it's a temporal version of Conway's law. It tells us that much of our complexity comes from the past. The state of a system reflects not only the organization, but the organizational history and flow of people. What I mean is the structure of the software reflects the organizational structure integrated over time. It's a really important insight. Rather than just looking at the stasis, let us also look at the past and how that has left this kind of impression. But speaking of impressions, I don't want to leave you with the impression that all the complexity is just the team or the kind of code decisions that we make. Some of that does come from the essence, the essential nature of your software. So in domain-driven design, there's a kind of an interesting point that Eric Evans made. Domain experts should object to terms or structures that are awkward or inadequate to convey domain understanding. There's kind of a feedback cycle here. Are we talking about the same thing? Are we building the right product? Importantly, developers should watch for ambiguity or inconsistency that will trip up design. A lot of our complexity comes not from developers. I mean, a lot of it does, but I want to say it's not exclusive. The domain is also a cause of this. So we are heading towards dinner. Now, dinner is a fascinating word because it means different things to different people, and it has a regional variation. To the degree, I won't say it was the end of one of my relationships, but it certainly didn't help it. A number of years ago, before mobile phones were kind of a thing, my girlfriend, who's from up north, so I was originally from London, and she said, "Why don't you come round for dinner on Sunday? I've got some friends coming round." I said, "Yeah, sure." I turned up what I thought was early, being a Londoner. 6 o'clock is incredibly early. And she was in a really foul mood, and I couldn't work out why. And then kind of like, her cooking's great, and it's just like, "So where are your friends?" She said, "They came, we waited for you, and they left about 5 hours ago. We ate the food." Turns out dinner has a slightly different connotation in the north of England to what it might do in the south of England. The word dinner is not unambiguous. At this point, we might be thinking of dinner this evening. The speaker's dinner is at 7:30. Now, that is a particular turn of phrase that is particular to the UK, Ireland, New Zealand, and Australia. It means this. There are also a number of people in the room who go this. Because if it were German, you'd be going 7:30. Yeah, it's half before. This is very common amongst languages. We can use the same words and actually be having a completely different conversation. We can miss each other by 1 hour or many hours. What is also interesting is the dependency of context. Because when I said 7:30, you might have been thinking whatever, but you weren't thinking 7:30 or 6:30 this morning, but that's also 7:30. The point there is the context that you're in will influence in ways you cannot comprehend. Of course, if you're from North America, you're probably sitting there going like, well, 7:30 is 3.5, what's the fuss? So we have a great deal of complexity that is baked into the domain. Some of that complexity is historical. Good afternoon. It's not the good that I want to focus on, it's the afternoon. And specifically, noon. This word, it's one of those things, you pick it up if you're a native English speaker at a point you can't even remember. If English is not your first language, there was probably a point that you were told midday is also known as noon. That's where the word afternoon comes from. That's brilliant. Where does the word noon come from? It comes from the Latin nona. Oh, okay. So what does that mean? Well, if we consult the source, nona, feminine, singular of nonus, ninth. What? The ninth hour of the day, reckoned from sunrise according to the Roman method, which is about 3 o'clock in the afternoon. So yeah, it's still early afternoon at this point. The point here is that we have this baked into our domains without even knowing it. And those of us who are sensitive to it kind of pick up on it every now and then. You know, what have the Romans ever given us? Well, you know, there's the month names, which are, you know, these are drilled into you from childhood. You know the numbers, you write them down, you use that form. And it kind of makes a certain sense. There's a bunch of these named after gods. Janus, clearly the beginning of the year, because Janus is a two-faced god who represents beginnings and endings, looks to the past and to the future. Clearly that's the beginning of the year. Only one problem. In Rome, March is the beginning of the year. I mean, they loved festivals, but March is the first month of the year. So if you count this off in Latin, you do that. Actually, let's count it off in Latin. Which is really interesting because then we get to month 7, 8, 9, 10, which that's an off by 2 error for us. A lot of people don't think about this one. It's just like, why is the 9th month called 7? The domain, this is a mistake. This is a piece of hard coding that goes back 2,000 years. So when people tell you don't hard code numbers, this is the best example we have. So here's the point. So I finished this book under lockdown with Trisha G, JetBrains at that point, 97 things every Java program should know. Don't think there's going to be a C++ program should know. We've kind of probed into that one. But brilliant piece by Kristen Gorman. Answering the question, what time is it, depends on the location of the sun in the sky relative to your position. That seems reasonable, along with the political decisions made in that region up to that point in time. Oh, that seems a bit tricky. This is your domain. Date, I'm just picking a small domain, date and time. That's trivial. Everybody understands that. No, you don't. You have no idea how complex date and time are. I mean, you're sitting there going like, yeah, sure. So let's pick some examples. All the subtlety in this domain. I'm using this as a domain because it's kind of representative of almost every other domain, whether we are dealing with people, whether we're dealing with taxes, whether we're dealing with games, whether we're dealing with medical equipment. So Miguel de Cervantes, great Spanish author, died 23rd of April, 1616. William Shakespeare, English playwright, died 23rd of April, 1616. Spooky. This is why it's also International Book Day. There's only one problem. They didn't die on the same day. And this is one of those things, but you're going like, but you just said they died on the same day. No, that's not how it works. 365 days in a year. To the point, we drill this into children. Even Microsoft drill it into their product names. I mean, they're not going to call it, you know, Office 365.2422, roughly. I mean, that'd be great. That's, you know, that's the actual solar year, the synodic year. So we throw in a 366 every now and then. Back in the time of Julius Caesar, it was nice and simple, every 4 years. Yeah, not close enough. Not bad, but not close enough. Gregorian calendar, Pope Gregory the whatever. That's a little more complex. It defeats most people because it involves an and an or, and a not. I'm sorry, that's just too much for human beings. We can do lots of ands together, a bunch of ors together, but you start mixing the operators and it's, no. People make mistakes on this one. That gets us pretty close. That's not bad. Honestly, by the time it matters, we probably will have destroyed the climate enough that the seasons will have drifted so far we don't care, or we will have transcended to a higher state of being and just be plugged into Netflix or whatever is coming in 1,000 years. The point here is the 23rd of April, 1616 in England was actually the 10th of May, 1616 everywhere else. It turns out that the term date and day, when you say the same day, it means something different to the same date. This is the subtlety that exists within our domain. This is just a simple domain that I think we all think we know. So what's interesting is that date-time handling is hard enough, but what happens when you give it to what happens when you give it to developers? I see this complexity. That's the essential complexity. You can't negotiate that. You can't unilaterally say, we have decided that it will be much easier if every year was 365 days and there were no leap years. There, I am developer, I have made it so. I'm sorry, it doesn't work like that. This is the non-negotiable bit. The bit we can negotiate, do we make it simpler? Well, no, we don't. Okay, so I'm going to pick on the C standard, which at a C++ conference means everybody feels really good about the fact that they weren't involved in this and that they think of this as the past. The problem is that everything is built on C, and most of C++'s sins come from here, and the same for JavaScript and Java. It turns out this is surprisingly influential, but it is also representative of the kinds of decisions that people still make. So let's just have a quick look. This is how we tell date and time in the TM struct. And I want to focus here on this one. This daylight savings time flag is DST. Is DST. It's listed here as int because, yeah, C didn't really have bools until relatively recently. I mean, 1999, but that feels recent in the history of C. But yeah, I know how to use Boolean. It's intended as a Boolean, right? So therefore, if today TM is DST is true, we are saving daylight. Otherwise, winter is coming. I have bad news for you. It turns out that isDST has 3 values. It might be called is, but it's 3-valued logic. It's greater than 0, yep, daylight savings time. 0, no daylight savings time. Less than 0, daylight savings time information was not available, which if you read it as a Boolean, because the name tells you it's a Boolean, you are likely to make the wrong decision. Most nations and states in the world do not use daylight savings time. So statistically, this is also kind of bad for you. You will read not available as yes, there is. I'm sure people know this quote and love it, but it's always worth reminding you. There are only 2 hard things in computer science: cache and validation and naming things. If it had just been called, honestly, DST flag would be better. But is DST, that's how we name Booleans. Let's go back to this. This was already tough enough, but at least we don't have to deal with the old numbers. Oh no, I am C. I shall number from 0. But only sometimes. I shall use both conventions. This has been a source of immense confusion over the years that has made its way into the JavaScript. Well, in fact, it's almost universal. Every now and then somebody comes up with another date-time library and says, I've solved the problems. That's brilliant. You haven't, because we are programming in the past. You have certainly allowed me to create some new stuff over here, but in as much as I have to deal with the old stuff, that complexity still interferes with my understanding. But we do eventually get it kind of right. So we have this kind of dichotomy. Honestly, I'd just say pick one. I almost don't care which one you pick, but don't pick both. However, I was always impressed by Stan Kelly-Bootle's suggestion. Should array indices start at 0 or 1? My compromise of 0.5 was rejected without, I thought, proper consideration. The point here is that sometimes people justify the month thing by saying it's a table lookup. You've just told me an implementation detail that is irrelevant and actually does not give you that much better performance on a machine in the early 1970s. But it certainly confuses people. We have other sources where we try and respect the domain. Days since January, the year day, that counts from 0. So we do account for 366 days. That's really good. Unfortunately, it turns out this is not enough. So Italy, the Polish-Lithuanian Commonwealth, various parts of the Holy Roman Empire, France, well no, actually France went a bit later, all jumped from the 4th of October 1582 to the 15th of October 1582 when they jumped from Julian to Gregorian. This was the slowest calendar rollout in history. Britain and its dependent territories jumped in 1752 from the 2nd of September to the 14th of September. Denmark and Norway went in 1700. Turkey went earlier the last century, as did Russia, hence the October Revolution was not in October. It is the slowest rollout. But I want to talk about Sweden. Any Swedes? Hey, you guys have got the best calendar. It's actually called the Swedish calendar. So they went from 1753, 17th of February to the 1st of March. But that was the second time they tried it. The first time they tried it was in 1700. They decided, because we don't want to be like the Danes, we are going to gradually adopt the Gregorian code. We're going to gradually adopt, one day at a time. What we're going to do is undock from the Julian calendar, and over a period of 40 years, we will slowly drift towards the Gregorian calendar, by which time we will have synchronized in 1740. And we will do this by omitting leap years. And so we will gradually drift between the two calendars and be wrong for 4 decades with respect to two. This is kind of like, I will say the Swedes did learn their lesson in 1967. It's kind of like, right, we're going to change signs of the road. Should we do that over a period of decades? No, we are doing it over the weekend. That's it. Everybody stops and we change signs of the road. So well done, learning curve adjusted. So they dropped the leap year in 1700, but they forgot to do it in 1704 and 1708 because they were having a war with Russia. That appears to be an enduring theme in history. The Great Northern War, it was just a little bit too much bureaucracy because you didn't want your generals turning up in the wrong place on the wrong date because they decided they were following somebody else's calendar. Charles XII decided in 1712, you know what? Sod it. Let's go back to the Julian calendar for a few decades. And thus, there was a 30th of February. This is incorporated in this document, Februarius 30. This means that there were 367 days in the year, and therefore this constraint that is embodied in the C standard is actually violated by a calendar of a well-known nation, and it is in relative, this is supposed to work for that. So the point here is that we, even when we're trying to respect the complexity of the domain, it turns out the domain will always defeat us. It is always harder than you think. So there is domain complexity. So can we make it harder? Yeah, sure we can. Sometimes we can be simplistic. How many days are there in the month? This is a very popular solution. Doesn't actually fit on one screen, so let's resize it. I've seen, if not this code, I've certainly seen this code, but I've seen other kinds of code. I'm sure you have. Somebody starts out and they say, right, okay, I've got all of this, and they come up with all these, I've discovered the switch statement. This is really rather painful. We like to call it enterprise code. This is very popular if you're being paid by the line of code. We might recognize there is a little bit of duplication here and factor it down. Nice. Or we can discover that actually declarative techniques are more powerful. Let's just do it all with tables. Honestly, I really wish people would use lookup techniques a lot more. It saves a lot of control flow. It's also easier to check the correctness of. But then, so I would call this the sweet spot. But then some developers go, oh, you know what? I can do better than that. You see, Kevlin, I don't do any lookups. And there's no branching. So there's no failed branch prediction. It's, no. I mean, I will admit, I had great fun putting this code together, but no, this is just really, don't do this. Kernighan's law. Everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? And that was a trivial one-liner that happened to scroll off the screen if I put it all on one line. But the point is, I'm sure that you have seen solutions and perhaps even created. In fact, I'm going to say I've certainly created stuff like this. So we need to understand that there is kind of a challenge here that we need to rise to, which is that when we look at certain elements, we need to understand where we have added complexity. So Alex Stepanov, lovely quote, generic programming has nothing to do with templates or template metaprogramming. He did not choose the word generic in that sense, although that is often what it means. in that context. Parameterized polymorphism. He meant it in the sense of the word general. Remember that word? It's very difficult. It has everything to do with algorithms and data structures. Unfortunately, the term was kidnapped and is frequently used to describe the clever use of templates. I love that term, kidnap. I mean, you know where he's coming from on this one. It's just like, yeah. And you know, I've been guilty of that myself. Yeah, in fact, very guilty. So let's just take a mild detour into language. And the answer to life, the universe, and everything. There it is in decimal, 42. There it is in hex. Octal, not relevant. The only people, in fact, I was reminded today, Walter's talk, that the only time you ever need octal, I mean, it used to be important, but the only time you ever need it is chmod. There are languages now that don't even dignify that. But binary, oh my God, if you're doing systems program, you absolutely need a binary form. This is essential. This is one of the most obvious things. And yet, it was not in the C language. It was not even in the C++ language until C++ 14. Do you know what the rationale was? The C rationale in 89 and 99 was a proposal to add binary constants was rejected due to lack of precedent, which is clearly nonsense. I'm not saying, oh, but lack of precedent. See, no, look broadly at all the other languages. But also an insufficient utility. Now, I respect the work of anybody on a committee, but if you're a systems programmer, you kind of need binary. It's kind of useful. So this is astonishing. So it looks like C will actually get this stuff in the next C standard, which I think is next year. But this is astonishing. This shows a disconnection. I mean, you know, I'll have to quote this, and some of you who are committee members, next time you disagree with something that's happened on various subcommittees, I invite you to use this. A committee is a cul-de-sac down which ideas are lured and then quietly strangled. Now, that's very harsh and very negative, but I'm also saying that because I've been involved in various committees. And it's one of those things, sometimes you end up with the magnificence of group intelligence, and other times you end up with groupthink. There's a wide amplitude between those two, and you're not sure which day you're on. It turns out collectively we can make some profoundly blind decisions. It turns out that there is a sweet spot when dealing with complexity. But let me just talk about why I'm putting this here. Because so template metaprogramming was discovered by accident in 1974 by Irvin Unruh. Within 2 years, lots of us had discovered you could do lots of things with it. So I wrote in 1996 a template to allow me to use binary values. It still compiles. I checked it. I just thought I had a bit of fun yesterday. It's just like, yeah, okay, I've got a bit. I've got a struct for a bit. I'm going to specialize it for 0 and 1, but nothing else. And then I'm going to have bin for binary, bin of 0 is 0, and then everything else is decomposed, and it works really well. And you can pat yourself on the back and go, yeah, that's really good. Nice template metaprogramming, that's really cool. The fact that you have to do this at all, and the fact that I enjoyed it, is kind of a guilty pleasure, but it shows the complexity. If I wanted binary digits, what I would end up having to do. So let's close with considerations of the complexity that we get from some of the base level things, like the programming language, that is almost sometimes blind to us when we're thinking about the grander architectural view or the nature of the problem domain. That's one of the challenges of software development. There is so much that can give us complexity, but it comes from the language as well. What the language does or does not do, or what its culture invites us to do. Now, John Backus was the lead on the development of Fortran. But as far as he was concerned, Fortran was an experiment in the 1950s to prove that you could actually create a high-level language that would produce code that was comparable to what a human would produce by handcrafting the assembler. At the time, it was generally believed this was not a thing. So he basically set out to do it. Fortran had there was no deliberate design thinking in it, except can we create something that produces efficient code? Which is why Fortran's, for those of you that are familiar, for those of you who are not familiar, you don't want to be, it's a great piece of history. But there's a lot of accidental design decisions there that were done in the name of efficiency. Now, John Backus moved on from that. He was a little bit surprised that the rest of the industry didn't. 20 years later, he received the Turing Award, and he was talking about, he said, conventional programming languages are basically high-level complex versions of the von Neumann computer. He said, note the word complex. We've just exchanged variables for storage cells. We've just exchanged jump statements for a variety of control flow. He said we kind of beefed it up and added a lot of paradigm soup around them. But ultimately, we haven't really broken away from those basic things. And when we look at language evolution, and I want you to remind you, he was saying this in the 1970s, programming languages appear to be in trouble. It turns out being in trouble is not the same as it's the end. We can be in trouble for decades. Each successive language incorporates with a little cleaning up all the features of its predecessors plus a few more. So you may be familiar with if you're not familiar with XKCD, hey, what were you doing during the pandemic? I mean, you should have been able to read all of the XKCD cartoons. If not, welcome to XKCD. Nerd hardcore. But this is one of the classic ones. Fields arranged by purity. Sociology is just applied psychology. Psychology is just applied biology. Biology is just applied chemistry, which is just applied physics. Nice to be on top. I have a physics degree. And some of you are probably mathematicians. Oh, hey, I didn't see you guys all the way over there. Yeah, lambdas. I love the fact that people have been getting excited about lambdas, which were invented in 1932. We're now programming like it's the 1930s. Cool. I wonder what the next big trend is. Maybe, to quote John Lee, the observation change always comes later than we think it should. But maybe it's coroutines. Coroutines, this wonderful paper, describe our subroutines at the same level, each acting as if it were the master program, when in fact there is no master program. I love the zenness of this statement. There is no program. Forget spoons. Let's talk about coroutines. The coroutine notion can greatly simplify. Imagine that, introducing coroutines and simplifying things. This is really cool. I wonder who wrote this. Oh, Melvin Conway, who invented the coroutine in 1958. Wow, C++20, well done. Or is it well done? Because it turns out coroutines have been around for a very long time. Bliss, a systems programming language from the 1970s, is a really elegant, simple model for coroutines. And it's totally general. The body of any function may be activated as a coroutine and or asynchronous process. It's orthogonal to the core concepts of the language. They put real work into this. Biana worked on a little bit of a hack here, but he got something that was like the Simula model. Simula, the original object-oriented language from 1967. The first real code to be written in C with classes was the task library, which provides Simula-like concurrency for simulation. It's just like, yeah, coroutines. And then, I don't know, something happened. The 1980s, 1990s, cooperative multitasking went out of fashion. But suddenly it's refound a lot of excitement. So let's just close with an example. So I'm going to this year's Fibonacci convention. It'll be as big as the last two put together. If that's not bad enough for you, there's always this one. What did you think of my new Fibonacci joke? It was as bad as your previous two Fibonacci jokes combined. For those of you who are still not with me, the Fibonacci sequence. So how do I do this? Well, let's use C++ 20 coroutines. I've got a stateful function. My expectation was that coroutines would build on functions, or they would build on objects, or they would build on lambdas, or they would try to be as close to something that already exists in the language as possible. You know the funny thing about assumptions? They're mostly wrong. So I was incredibly wrong about what it would look like. But that looks fairly plausible. I mean, you can run it. You can see that we've added a few things. So we're now messing with keywords. So we decided non-library. Okay, fine. Should we have followed a different path? Good question. I'm not going to deal with that here. A lot of good work was put into it. But good work does not necessarily mean good results. The results I get, legitimately, that all works. And it looks an awful lot like what I would do in Python. There's a lot of languages that have embraced coroutines, but C++ has done it differently. Because that's not the code you need to write. Because that code won't work. Because C++ didn't finish the job. Given that we were talking about Sweden, let's go to IKEA. I think it's absolutely shocking that we've ended up with a whole load of stuff. We're actually getting a lot of stuff these days that's just like, a lot of good work, but we'll finish it in the next, no. Try something simple that works and is complete, and then do the clever bits later. Because we don't know what edge cases are actually legitimate. In order to get that simple piece of code to work, I have to go and put all this boilerplate in. And some people go, oh, but Kevin, you can get a library for that. Yeah, it's called the standard library, and apparently it doesn't allow me to write coroutines. It just says, here's half an idea. You figure out the rest. That's a really interesting contract, and not one, this is a failure to learn from the past. In C++ 98, there were a whole load of things that were put in that were speculative. And people said, oh, we don't want to do that again. Boost was created. Let's actually get real-world experience and find out what people are actually using. Whilst Boost is not perfect, it offered a migration path for many things that had experience put into them and had the corners knocked off them, and people actually used them and told you what was and was not used. And the danger is that we've created a structure and a complexity that can take us the opposite direction. So yeah, that wasn't quite what I had in mind, because I've looked at a lot of coroutine models. C++ wins the competition for the most complex. Now, that sounds like a language rant, because it is. I said I'd keep the language rant small. But the point there is a cultural thing. We have learnt to love complexity. So I'm going back to Sweden here. It's Stockholm. Specifically, I want to talk about Stockholm Syndrome. This is nothing to do with C++, this is to do with software development in general. Condition in which hostages develop a psychological bond with their captors during captivity. I deal with a lot of different programming language communities and a lot of different systems. Everybody becomes wed to their complexity. JavaScript programmers have a special soft spot for certain things that are complex. C# programmers have a different soft spot for different things that are complex, and so on. Everybody has this because it's a side effect of ingenuity and imagination. We should acknowledge that, but at the same time, we've also got to figure out, how do we rein that one in? The late Edsger Dijkstra, and speaking of late, I am late, so apologies for that. I would therefore like to posit that computing's central challenge, how not to make a mess of it, has not been met. He observed in 2000, most of our systems are much more complicated than can be considered healthy, and are too messy and chaotic to be used in comfort and confidence. And I would urge you to think that we actually have enough experience. It's not a lack of experience. We actually, okay, we run the world. Software runs the world. That is both, I don't know, exciting and utterly frightening. But a lot of what has been done is the creation of complexity, not simply the accommodation of it. There is a ridiculous amount of skill in being able to say no to your inner complexity instincts. It's really hard to do that, no matter what we're doing. Whether it's simple table lookups, whether it's that neat blog we just read and really want to use that feature. I've done that a number of times. I will not confess to all the sins of my past, but there's been a few where I've learned something going like, oh, I think I need to put that in this system. Does the system need it? Absolutely not. Do I need it? Well, in my heart of hearts, yes. That's the bit I need to address. So thank you very much.